Hello, everyone. So I hope my screen is visible to all. Yeah. So this session is going to be about understanding the basics of neural network. And what we are planning to do here is we will understand how neural networks are made from the very scratch, like how they are actually, built from the very bottom and what are neural networks. So I am doing this session. It's a part of DataHour series of analytics, Vidhya. Yeah, so as I told you, the contents of this session are we will first cover the basics of a neural network. What is a neural network? How do we make the neural networks? What inspired the concept of neural networks, right? Because I believe it is very important to understand this basics, to cover these basics, because in this field of AI or data science, what we tend to do usually is we tend to go towards more fancier topics, if I would say. We would jump onto computer vision, we would jump onto building BERT models, or jump onto building large scale NLP models. We would look at them, we would get confused, and we would be scared, and we will not be able to build large scale applications, we will not be able to build good applications. Why? Because we don't have the basics ready, we don't have a strong base for neural networks. So it is very important to have the basics very clear, right? So first we'll see the basics of neural networks and how do they work, and so on. And then what we will do is we will go on to see the implementation of those neural networks. So now, since we saw the basics of neural network, we'll start seeing how to build them. First we'll see how to build them from Numpy. When I say Numpy is a library. For some of you who do not know, Numpy is a library used in Python to perform array manipulations, or vectorized implementations. So we would basically, that means is we would implement a neural network from the very scratch, and then we would see implementation of a neural network on TensorFlow. Now, the main thing to note here is implementation. When we try to implement a neural network, right? I mean, if you go to Google and start searching implementation, how to implement a neural network, you'll get thousands and millions of results, right? The implementation is not very important. What is important is what goes behind the scenes, right? Like, for example, you'll see when we go towards the implementation part, you'll see when implementing from scratch, it is actually very difficult. Like, we have to make 2 3 functions, we have to make a dense function, we have to make a sequential function and all this. And when we use TensorFlow library, it becomes very easy, just a 2 or 3 or a 5 liner network. How do you put it into a coding part? Now, the most important part is the deep dive of neural networks. You should know that when you're calling a sequential function, or when you're building a layer of a neural network, what goes in building that layer, right? So that is very important, because you can build a code, you can easily get a code from Google or anywhere, right? If you do not understand what happens behind the scenes, it will not be very helpful, right? I mean, you won't be able to build efficient neural networks, right? So then we will basically see how a neural network, how training a neural network happens. We would see every step, and then we would see the activation functions, and why activation functions, I believe, are very important in a neural network. A small slide about me. So as I have 4 years of work experience in the field of ML, and I have built and deployed models in the domain of machine learning, where we did predictive analytics, we did sales prediction. I have experience in computer vision, where we used image segmentation and then classified those images based on use case. And then, some projects on NLP, where we built a question answering model, text classification, or entity recognition. And this is something that I have worked on. And what I like to do, what are my hobbies? I like to play tennis. I am a big football fan, and I like to read. I like to read anything. I like to read newspapers, magazines, or books. So these are my hobbies. Yeah. So I hope this slide is visible to everyone. This slide basically, first of all, just try to look at this slide and see what it actually means to you. I'll give you a few seconds. If you are able to derive anything out of this slide. Yeah. Yeah. So basically, like you saw, right? You must have heard, or you must have heard anyone saying, or you must have seen on the internet that how neural network or the neurons in the neural network are inspired from neurons in the brain. I would say it is partially true. It is true, but the brain is a very, very complex entity, and the research going on. There is still, needs to go more and more advanced, and brain is a very complex entity as compared to a neural network. But and if we have to say in a layman's term, I would say that a neural network or a neuron is slightly based on a neuron in a brain. So if we see a neuron basically takes your input from dendrites, processes it through nucleus, and then gives the output through axons, which later, which later basically connects the axons, then connected to the next nuclear and neuron, and then it forms a long chain. Similarly, if we see our neural networks, right, we see, let's consider this to be a black box, right? We don't know what is going on. A neuron in a neural network will take an input like here, and it will give you an output. Now the output is something meaningful to us, right? Like for example, let's throughout the series, let us consider the use case of house prediction. Given a lot of features about a house, for example, any features like what is the size of my house, is there a garden in front of my house, all these features, my neural network has to predict the price of my house, right? So given that, there is a black box which will take all these features, do some processing. We don't know the maths right now, and it will tell me, okay, your price of your house is 1,000 rupees or 100 rupees. I'm just saying, so like that, right? So what goes inside that neuron and how that calculation happens, and that is very important for us to know, right? Like we can start building neural networks, but if we don't know what the calculation is happening inside a neuron, it can be very tricky, right? So we won't know that. So basically, if we have to see in a neuron, we get some inputs, x to xn minus 1. You can see all these are inputs. Usually, we apply some weights and biases. These are all parameters of a neuron. So every neuron has some parameters, right? If you are getting confused, don't worry. We'll discuss this in further. What we do is we get the input, we do some mathematical operation in this circle, in this neuron, some mathematical operation is happening, and we get an output named A. So this is the very, very basics of a neuron or a neural network and how it works. Right. So we saw the basics of a neural network, and let's see a more complex neural network, right? Like how it is working. Let's go ahead. And so now we were at a point, we were trying to see what are the layers that go into a neural network, and we saw the basics of a neural network, right? So now we are here seeing, what is a more complex type of a neural network, right? So we earlier we saw it was just one neuron. It was getting an input and it was providing an output. In real world scenario, your neural networks would not look like that. Like there will be hundreds, and like there will be many layers in that, and each layer will have many neurons in that, right? So it won't be that simple, and it won't just be that easy, right? So if we have to understand what goes into that, let us just consider the image on the top left here. So we get an input, right? And this neural network has three layers to it, right? Layer one, layer two, and layer three. Usually the layers which are highlighted here are known as hidden layers. And this layer, the layer three, is known as an output layer. So hidden layers are something, these are our terminologies. Like somebody also tells, input layer is layer zero. It does not matter. All we need to know is we have three layers right now in our neural network. Two layers are the hidden layers, and the third layer is the output layer, right? So how does that work? So the first layer, basically what happens is we get the input to the first layer, whatever is our data set. In our scenario, it is the house price prediction data set. We will predict the house price of a house given some features, right? So what will happen is the input of all these features come into this layer, right? This layer does some mathematical operation, gives an output. This output, then the output of layer one goes as an input to layer two. Similarly, the output of layer two goes as an input to layer three, right? A sequential model, you all understood, right? Input of the previous layer acts like input of previous layer is here. So we can now see how this is sequential in nature. The input here acts as an output, and this output acts as an input, right? So what happens here, we have to see, like, so let's say this layer one, we have three neurons in this layer. And like we discussed, I told you earlier, right? Each neuron has some properties associated with that. In neural networks, we call them parameters. So these parameters, let's say each neuron has a parameter weights and biases, W and B. Now what happens is we get an input X, right? This input X is multiplied with the weight and then added with the bias. Very simple, right? W into X plus B. Whatever input we got, we multiplied with the weight of this particular neuron, added with the bias of this particular neuron, right? This WX into B then gets passed to a function. This function, right? The G of Z that you see here, let me, yeah, so this part, right? This part is a mathematical operation which happens. It's normal multiplication and addition, right? The input got multiplied with the weight and was added to a bias. Now what happens is this part gets passed to a function which is known as activation function, G of Z, right? Now that defines what will be the output, right? So let us not get confused over what activation function is. Let's say this part here comes up to be 120, right? This 120 gets passed to some function and that value becomes A1. So each neuron gives an output. So neuron 1 gives an output A1, neuron 2 gives an output A2, neuron 3 gives an output A3. So what happens is, this subscript 1 means that this is the first layer of the neuron, right? So what happens is we get an array which looks something like this: A1, right, A2, and A3, right? A1, A2, and A3. So the output of each neuron, that is the input multiplied by weights and biases, gets added and we get A1, A2, A3. So this A1, A2, A3, which is basically the A superscript 1 matrix or an array or gets passed to this layer now. So the input of this layer is the output of the previous layer, right? Very simple. We just did some multiplication, added a bias, passed this value to some function, and then we passed it to the next layer. That now we have done some processing on this data. This layer thinks that this could be the price of house. Let's pass it to the next layer. The next layer starts processing and takes the input of the previous layer. So if we see here, right, we did W into X plus B because X was the input here, right? So now here we do W into A1. If you see here, it's A1 plus B2. So W2 is the weight and bias of the first neuron, and we multiply it with the output of the previous layer. Very simple, right? The output of the previous layer is being used by the current layer. Simply, it will give us some number. We don't know it, right? Some number, let's say it gives us 100, right? It gives us 100 number, and this number is then passed to an activation function. It can be any function. Let's say it is doing this number, it takes and squares that number. So our function right now takes 100 and squares it. It can be anything depending upon our model, our use case, right? So this basically what it does is it did the W into input plus bias. It did that. So two neurons, we get two outputs, right? So again, how many, just try to think, how many out, what would the A2, this matrix or this array, if you can also call it, what would this A2 look like? Just think, it would be A1, again A2, right? And the superscript 2 here indicates that it is the property of the second layer, right? So superscript 2 here is telling that, this is the property of second layer, right? So A1 to A22. So we get this. Now this is again passed as an input to the third layer. Now the third layer is our output layer, right? So the output layer has to output one price of our house, right? So we had some features of our data set. Let's say we had features saying the price, square size of my house, is there a garden or not, how many doors does my house has, how many balconies does my house has, right? And based on that, we are processing that information. Input of layer one is the features, then output of layer one acts as an input to this layer, and so on, right? So similarly, very easy, right? One neuron, it will take A2, that is the output of previous layer as an input. And it will have obviously like I told you, right? Every layer, every neuron has its own parameters, right? That is why it is very important to understand why neural networks, why you have to change what parameters to change, how to optimize a neural network. This becomes very, very important, right? So you know that this is the weight of this particular neuron, W13, and this is the bias of this particular neuron, B13. Don't stress too much on what is weight, what is bias. Let's just say that this is just a parameter of a neuron. Every neuron, like our brain neuron has some properties. A neuron in a neural network also has some properties or a parameter, right? So W and B are some variables which are parameters, right? So W into the output of previous layer, and then it is added to the like some values added, and then we get A13. A13 is what will be the price. So we get after this, after passing this value again to some function that does something like that, that will, according to our use case, it basically will give us a price. So for example, let's say this model gives me a price that your price of your house is, let's say 1,000 rupees, right? So, okay, this is the price of my house. Now, very important thing to see is this entire thing that we saw, right? Going straight from input to layer one, then passing to layer two, then going to layer three and coming to the output is known as forward propagation. Like this entire thing is known as forward propagation. Very easy, right? So we just, every input, we applied some mathematical operation, we multiplied W, added B, and each neuron gave its own value, and then that was passed to the next layer and so on, right? So some of you who know Python or are well versed with basic multiplication or a dot product, they can see here, right, this part of the code and correlate directly to here, right? So what we are doing is W is total unit. So let's consider layer one right now, right? Layer one. And what we are doing in layer one, we are seeing W. So W11, B1. And then what we do is we calculate the dot product here. If you see right now, this line is doing this part. A11 is being calculated here. So if you see W into A in is the input, and then we add the bias. So we get Z out of it. And then Z is passed to a G of Z. G is nothing, but it can be any function call, right? Anything that you are doing. You maybe the value of Z, you are maybe squaring it, maybe you are square rooting it, or maybe you are doing something with it, right? Anything, or maybe you're just leaving it as it is. It can be anything, any function, right? So this does the calculation for each layer. And then how do we tie all of this together? We use a function known as sequential function, right? So in sequential function, we call this dense function. And if you see here, right, see the first layer. The first layer, we are passing X as an input. W1 and B1 are the parameters. We will pass those parameters. That is not something that is predefined. I can pass 0, 0, 100, 100, 200, 200. That is on me. So you will later see in the course, how do we optimize those values, right? So we pass those values and we pass the input. We get an output A1. A1 then becomes the input to the next call, right? And similarly, A2 comes as an output of this layer we saw here, and then A2 becomes an input to the next layer, that is our third layer. And in end, A3 becomes our output, right? So we saw here that how a complex neural network works, right? And this is at a very basic level, this is how a neural network operates. So you can add hundreds of layers, right? It will go in a sequential manner. I can add thousands of neurons here. It won't matter. Like every neuron will give that output. We would have a similar array. The output of this layer would go as an input to the next layer. It would be a similar thing, right? So this is why it is very important to understand this particular structure, right? So we'll go to the next slide. We saw the implementation here, right? That we take the weights, we multiply the weights with the input, we add it to the bias, right? And we get an output. So we call this function regularly. First, we call it with this, we get an output A1, then again we call it, then again we call this function, right? So you see, right, how this is the implementation of a neural network from very scratch, right? Like from the very basic, you're multiplying, you're doing the dot product, you're adding everything. So there is a lot of scope of error into this. If you get large amount of data, how will your function deal with that? If you get large X, large weights and biases, how will your function deal with that? That's where TensorFlow comes in, right? Now you see how easy to understand it is. So for those of you who do not know, TensorFlow is a library which was developed by Google to make the lives of data scientists easier, right? So what they basically did was they created a library and which would help us to build neural networks, right? So if you see, let me compare it side by side. So if you see, we were calling a dense function, right? This dense function every time. And similarly, we are using TensorFlow.layers.dense to create a layer, right? So we saw that we had layer 1 and then we had layer 2, right? Sorry for my drawing. But yeah, so we had layer 1, layer 2, and layer 3, right? So we use sequential. If you remember in the previous slide, we used a function known as mySequential to tie all these layers together, right? So what we do is we use a sequential function of TensorFlow to tie all these layers together, right? So first we define the input size that, this would be the size of my input. So the model now knows that, you're going to get an input of this particular shape, right? Then we define layer 1, L1, and then we define L2, and then we define L3, right? So what we do here is we tell TensorFlow that, make a neural network for me whose name is my model, right? Put 3 layers in that neural network, 1, 2, and 3. In the first layer, add 25 neurons, right? We saw that in this part, we had 3 neurons, 1, 2, and 3. So I'm telling TensorFlow, I'm just trying to show you that, neurons is something we can easily add with number. Once you get the hold of how to build a neural network, how to optimize it, these are numbers which you can add based on your use case, based on how well your model is performing or how bad your model is performing, right? So layer 1, I tell TensorFlow that, do what? Just create 25 neurons like that and 25 neurons in each layer, in layer 1, sorry. And then 15 neurons in the second layer. And similarly, 1 neuron, because my output is like that, 1 neuron in the last layer. Then I told you, right, each neuron gets passed through a function known as G. So G of 100. So I tell my model that, the activation function, this is known as activation function, the output of this neuron, pass it to a function, which is known as a sigmoid function. We will discuss what sigmoid function actually is. Those of you who actually want to know right now, sigmoid function is 1 upon 1 plus e to the power minus z, right? Z is nothing but this value here. So it becomes e to the power minus 100. So this becomes your output of your layer of each neuron, right? So each neuron acts accordingly, right? So this creates a structure of a neural network. Then we have to define a loss function, right? So what is loss function? We will discuss this again in detail, like right now. Right now, we are just trying to see how TensorFlow is making our life very easier, right? Literally with 4 lines of code, you have created a neural network with 25 neurons in each layer, right? And this could work pretty well for many scenarios, like even in modern day scenarios, it could work pretty good depending on your data. Then we obviously a neural network in one range of forward propagation. When I say forward propagation, going from start to end in one order, right? So start to end in one order. So basically, we tell our neural network that, we would get an output. Let's say in the first run, we got an input. This gave an output, then the output of this input, and then output. This again scenario, we got a final output, right? My model predicted the price of my house to be 10 rupees, right? But in reality, the data said that the price of my model is 1,000 rupees, right? So we have to tell our model somehow, right, that what you did was very incorrect, what it is totally wrong. So how will we do that? We tell TensorFlow that there is a method known as binary cross entropy. Use that method to optimize the values of W and B. Let's say our parameters are W and B. If you remember, I must have told you at the very start that W and B are something that we decide, right? So initially we would give some W and B values to the model, and it will be randomized, or anything, it can be anything, right? So these parameters of the model, obviously we cannot get them right in the first try, right? Because based on the data. So based on this, again, forward propagation, some values of W and B, our model will give an output. We would have some real value of that price, right? So, and based on that, we would know, okay, it is 900 rupees off. So what we need to do, we need to update weights and biases, and then it again goes back, updates those weights and biases, and then again starts running. We will discuss all of this. So what happens then is, one second, yeah. So we saw that, like, we tell the model to compile our model based on this cost function. And then we tell it to, if you see this, right, the forward propagation, the backward propagation, the forward, do it 20 times, right? So we then model.fit basically fits our model, and our model is now ready. So once our model is ready, we pass the new values, the unseen values of our data to the model. So new values of our house. So let's say some of you want to know the price of your house, right? You don't know the real price of your house. So you pass these values of parameters of your house, and our model will predict. Hopefully, if we have given a good cross entropy, if we have given good optimizers, if the number of layers are correct, our price will be as close as possible, right? So, like, the what I told you right now was on just a larger scale on how TensorFlow, or that's why I told you, right? Coding a neural network is not that big of a deal. TensorFlow can do your job in like just few lines of code where you have to write NumPy functions and your all functions. And what I have seen usually is these libraries such as TensorFlow or PyTorch, they are very advanced, and they will get more advanced as the time progresses, as the computation power improves, as more and more people know data science. These libraries, maybe some of you might create your own libraries, and these libraries become more and more advanced. So coding part becomes more and more easier for us, right? So what changes to build efficient systems or efficient neural networks is you have to know which neurons to use, right? How many number of neurons to use, which entropy function to use, which optimizer to use, how many epochs to run, right? These are the parameters of the model, how to update the weights and biases. That is something that is in our hand, right? So we need to know for large scale systems how to improve our model, because coding is something that can be done very easily, right? Once you get the hang of it, you can basically do even a Google search on it, right? So basically, if I have to say, training a neural network or training any model, right? Any model, be it a random forest model, during my course of the experience that I have, these three steps is what I have largely followed, right? So these three steps is basically like whenever you have to train a model, any model, not only neural network, we follow these three steps. Like number one is always to define a structure of our model, right? So if you saw here, we defined a structure of our model. So number one, we define the structure of our model, right? We tell that, once we get an input, any input, let's say it is an image of a cat or a dog, it is the features of my house, it is my credit card history, right? Anything, my browser history or anything, right? To predict whether my email is a spam or not. Anything, right? We would, be it any type of model, anything, we would first need to know, right? We are getting an input, how will we process that input and how will we get that output? It is very, very important to know the structure of your model. Once that structure is in place, the next most important part is how will we define the cost and loss function, right? Like your model gave an output. How will you know whether that output is correct or not? You need to know if your output is correct, if it is wrong, what is it doing, how well your model is working. And the third step is so that you can, once you know your loss, your cost is very, very high to train that model. You will try to obviously reduce the cost, optimize the model. Now you must have heard, like you will hear this term a lot, optimization of the model with respect to parameters. This means, this is just a fancy term. It doesn't mean anything big. It means, I told you, right? It means we optimize the model and we have those parameters, right? The weights and biases. These are the parameters. So how do we optimize the model? I told you, right? These parameters are what these are in our hand, right? We know how to, we can change this, and the model's efficiency will improve or it will decrease. Right? So based on these parameters, we try to optimize our model. So if you see here, we are trying to, this is what it means, optimization of your model with respect to the parameters, right? So these are the three steps which we largely follow. So let's see, how these steps are relating uh, to our neural network, right? How well, or in our use case of doing a price prediction, how these three steps fit in. Okay. First step we saw was to build the structure of a model, right? We saw in the code below before that this is basically the structure of a neural network. So what I did was I told TensorFlow that, please create a sequential model. Sequential means it will go in a straight line, do forward propagation, come back, do backward propagation. Create a sequential model. It should have 3 layers, right? It should have 3 layers, and each layer should have 25, and then second layer should have 15 neurons, and the first layer should have 1 neuron. That is what we do. First layer, it is done. We defined the structure of our model, right? So the first step of building your model is now clear. We have defined the structure, and now we can, once the structure is ready, we know that, we will get an input of shape 400. We are done with that. It will go to the first layer. It will have 25 neurons. The output of this layer will go to the second layer, which will have 15 neurons. The output of the second layer will go to the third layer, which will have 1 neuron. At the end, I will get an output. And the name of my model, put it as my model, right? Anything, you can put anything. So we have defined a structure. What next we had to do? Now output is coming, right? We have to improve the model. So how will we do that? We do that by defining a loss and a cost function, right? So it is very important to know what is a loss and cost function, right? So loss is basically, what we do is we get a predicted value, right? We get a predicted value, and we always have a real value, right? We know, like if we are training a data on model, we would always know, we would have the target values, or what is the labels, I would say, and then we would have a set of features, right? So let's say while training our model, we had a data set which looks like this, and we had some features here, and the first row said the price is 100, the second row said the price is 1000, and let's say it is only 2 record data set, right? So this is how we pass this entire thing to our model. And so model knows, okay, these are the features and this is the value, this is the real price. So we somehow, like in my use case, right, in the housing price prediction, my model predicted 10 rupees, right? But in reality, the price was 1000 rupees. So we need to somehow, this is a very, very bad performing model. So we somehow need to, improve the cost of this, or improve this model. So what we do is we define different cost functions. So there is a huge amount of maths which goes behind these loss functions. I'll try to keep it as simple as I can. So these cost functions, or these loss functions are use case dependent, right? So for example, if my use case is binary classification, right? I want to tell whether the email, let's say I'm getting, is a spam or not, or whether, anything between 0 or 1, whether this product will sell or not, or whether anything like, right? So then we use a loss function known as binary cross entropy. For example, in our scenario, when we are using a mean squared error, when we are predicting the price of our house, that is, it is a number, it is a regression problem. right? We use mean squared error cost function, right? Very simple, right? And don't worry, nobody remembers the name. These are some very basic cross function like cost functions. Mostly people go to the Google and search, then what is the cost function? What will be the loss for my use case? If I have a multi-class classification, what will be the loss in that scenario? What will be the loss in binary classification? So those of you who did not know what binary classification would be, it would be predicting between two values, 0 or 1, true or false, anything, right? Mean squared error is a regression. When we have a regression problem, then we do that, right? So regression problem means when we have to predict a number, right? What will be the weight of a person? What will be the age of a person? Or what will be, let's say, the price of my house? Those type of things. So like I told you, like if somebody is actually interested in how a loss function works, this is an example, right? So this is, if you might have seen the logistic regression, like some of you who know, some of you don't know, don't worry about it. Binary cross entropy and this loss function is exactly same. What this does is it's a simple mathematical formula in Y. Let's consider this particular scenario, right? When my model predicted 10 and the real value was 1000, correct? The Y is the target variable. We put 1000 here. Fx is basically the output of my model. What output did my model give? 10 comes here, again 1000 here, 10 here, right? So this will obviously, it's a mathematical equation. It will give me some value. Let's say it gave me 25. Any value. I'm not going into the very details of it. It will give me some value, right? So we would know this is the loss of our particular model, right? So basically, if you see here, loss, it can be any function, right? L is some function, binary cross entropy, mean squared error. All we do in a loss function is we compare the prediction of the model to the target variable, right? So that's what we do here. Nothing major about it. We just compare the real value with the predicted value. And then we calculate, what is the cost. Cost is so those of you who know high school maths or some maths, this function basically means summation. So loss we did for one row, basically summing over for the entire set, entire examples, we get a cost, right? So basically comparing the output with the target, right? And then how well the model is doing, we get some JWB, right? So this equation, like Fx, if we all knew, was G of W into X plus B, right? And then this gets passed into the cost function, right? Those of you who are getting scared with maths or who are thinking that this is too much to grasp, do not worry. You just need to know what loss and when to use, right? And basically how to optimize that particular loss. Okay, so this was the second step. And I would say one of the most important steps to define the loss functions, right? So now our model knows with model.compile, our model knows that, this is the loss of a particular neural network which we had built, right? So next step is we know, right? Okay, so in my case, my model now knows that, the loss is very, very, very high. So we need to do something, right? We need to do something to improve the model. So we will see in next slide what to do. So then the third and the final step comes optimization of the model, right? So we have defined a cost function, right? And we try to minimize the cost function with respect to parameters of the model. In our case, the model has parameters W and B, right? Each layer of a neural network had neurons, and each neuron had W and B present in it, right? W1, W2, W3. Some variables, some functions, we had given them some values initially, random values, entirely random, right? So we defined the cost function now, and we know that, the losses or the cost is very, very high to train this model. So what we do is now we have to, do something, right? So what we do is we try to change these values of B. And how this happens is, let's say this is the plot of our, we are plotting the cost versus one of the parameters. And our purpose is to come at the minimum cost. Let's say the cost here is very less, like 5, 10 or something. And this value of W, this is the purpose for a particular value of W to come at the minimum possible cost, right? So that is what we do in an algorithm known as gradient descent. There are many optimization algorithms, but I believe knowing gradient descent is of utmost importance, right? Because gradient descent is somewhere, you know that how your values will be updated, right? So what gradient descent does is, let's say this is the graph of our model. We take this, we go a value down, we go a value down every time. You see right here, let's say our model ran first time, the value will be something here. Then model knows, okay, the cost is very high, so we have to reduce the cost. Then model comes here, okay, cost is better, let's see, can we improve it further? Okay, we can come here. Okay, so the value comes here, and then we see, okay, the cost has reduced, can we even go further? Can we even go further? We go, and then we arrive at this particular point, which is W. Let's say it is any value. Let's say this is 10 and the cost is 5, right? So now with this, we have achieved the minimum value or the minima, or we have achieved the minimum value of the cost. Okay, so how does that work? Right? This algorithm known as gradient descent helps us in that, right? So this value, some of you who might know what this is partial derivatives. If those of you who do not know, no need to worry about that. It is just to understand. If you understood this part of the graph, that our basic purpose is to keep updating W time and again. So we ran it, let's say 20 times here, 1, 2, 3, 4, we ran it 20 times. And then in those 20 times, we arrived at this particular W. That is what gradient descent means. Those of you who want to know a little bit more maths, or who want to know how it is working for every layer, for every neuron, this is how gradient descent works at the backend, right? So gradient descent, basically, let's say we have a layer L, each neuron J, right? It updates each. So I told you, right? Every neuron J has a W and B associated, right? So all of this will have a W and B, W1, W2, W3, W4, right? And this is layer one. So for layer one, in in the first neuron, whatever was the value, update this, do a partial derivative of the cost function, and update the value of W. So basically W is equal to W minus some constant. We will see what that constant is. It is known as alpha, and then do dj by dw, right? If you see here, it is dw, here it is db. Those of you who know what partial derivative is, or what derivation is, or how do we calculate derivatives, you will know that we are basically differentiating this with respect to W and with respect to B. Those of you who do not know, no need to worry about that. Just we are, let's consider this to be some value, and we are doing W is equal to W minus some constant, and then doing dj by dw. So this runs for, let's say we define, these steps, right? 1, 2, 3, 4, we ran 20 times. We define how many times it can run. We define, run it for 20 times, run it for 200 times, run for 2000 times. It depends on us. So for every layer, let's say for layer one, for neuron one, right? It updates this. And now what is this thing alpha here? Alpha here is known as learning rate. Learning rate, if we have to compare it, right, in the graph sense, learning rate is how big a step you have taken, right? So we took this step. So basically it is just a value which you define, but how it helps us is, it helps us to achieve W faster. Let's say W is W minus our learning rate is 100. It's a very big learning rate, right? What will happen is we would start taking very big steps. We would come here, we would come here, we would come here, and then we would keep on oscillating. We would never reach this point, right? And let's say our W is very small, like 0.000000001, right? What will happen is we will take too much of a time. Instead of these many steps, we will keep on running. We will take like lots of time to achieve at this part, right? So this is what alpha does. Alpha helps us in the magnitude of the steps that we take towards coming in this direction, right? So this is what optimization of a neural network is. right? So we do this for every layer, right? We do this for every parameter in a layer. Like you saw, for each layer, for each neuron, we try to optimize each of these values. Let's say now this is a very, very basic neural network, right? We have defined only two parameters to the model. Let's say you come across some model which has three parameters, four parameters, five parameters, and then you can put these parameters, you can define this, right? So this all to me, it looks very, very scary, right? To what is partial derivatives? How do we see the cost function, right? What we do here is TensorFlow does all of this for us in the model.fit stage. We tell it that, run this entire process 20 times. Run this entire process. If I put 200 here, I would tell, run this entire process 200 times. The forward propagation, backward propagation, updating, run it 200 times. So this is what this model.fit does, right? Like I told you, TensorFlow or these libraries have made lives of developers or data scientists very, very easy. But you need to know, right? Like, let's say you did not know, like your model is, let's say, not performing well, right? You simply copied from the internet, or maybe you just knew that, model.fit is the final stage of the model. You did model.fit x comma y epochs equals to 20. Now your model is not performing well. Why? Because your weights and biases are way off the charts. It is somewhere here, right? So you knew that, you have given, so now you know that, this is a step which I can do. Like, I can actually change the number of epochs so that, model will start training, model will become better. But as we all know, like too much of everything can be bad. Like if we put it, let's say 2000 or 20,000, right? It does not mean that the model will become very, very good, right? There is a limit to how good a thing can be, right? Because if it is here, it can always go in this direction again, right? So it can always go in this direction. Just to understand, right? It can always go like this. So there, basically, right, that this is one parameter which I can change now in TensorFlow. Even if the code is there, now you will know, right? I can change my epochs. I can change the number of layers. Maybe you are thinking that even changing epochs is not helping. Let's try increasing the number of neurons, or maybe decreasing the number of neurons, so increasing more layers. Now you will know, right, what happens when you do that. If you increase alpha is again one of the values which you can define. If we see here, one second. Yes, so this is not a gradient descent. This is an Adam optimizer. I will explain that also in a step that we define again a learning rate here, right? So we all these parameters are something that we define on our own. So now we know, number one, we knew that, okay, we have defined a structure. Now we know what is the cost of our neural network. And now we have optimized our neural network also. Now we will simply call the predict, and our predictions are ready. And we can easily now predict the price of houses, see the weight of people, or maybe guess the ages of people, or anything, right? Price of share market, or anything you can start doing. These are different flavors to a neural network, but now we know the basics ready, right? Okay, so like I told you, right, activation functions. Activation functions are again something which are very, very important to a neural network. Like we saw, right, in each layer, each neuron, right? Let's say this neuron did W into X. Let's say the input is X right now, and it did B. It gave us 120, right? But based on our use case, right, you will know later on when you start researching more into how the use cases are, what are different types of use cases, how you want to change your output, right? You will define an activation function. So what activation function is there? Let's say my activation function does nothing. It does x square, right? G is equal to x square. So I pass 120 to this, and it becomes 120 square, right? So this will be the output, G of Z. This will be the output of my neural network, right? So it becomes very easy, right? Now we know what activation function does, right? So as I told you, some use cases might require different versions of activation functions being applied to a neural network. We will see what are those different type of use cases in the next slide. So we apply, like I told you here, right? We are applying activation functions to the output of a neuron. Basically, the activation function helps us to decide the output of a neuron, right? A neuron did some mathematical calculations. It went to the activation function. Finally, activation function decided, that this is the output of our neuron. So this became very simple to us, and we passed an input, and then it gave activation function gave an output. In our scenario, it gave us 14400, or if it is square root, it will give square root, anything, right? So in very general or broad sense, and not to confuse you a lot, there are two types of activation functions, a linear activation function and a non-linear activation function, right? Let's say this neuron, or don't confuse that in one layer, I can give different activation functions. This is, okay, let's create a separate layer. And I created this layer. It did WX plus B, right? Let's say my use case does not require any activation function to be applied, right? I don't want to apply any activation function. Let's see how that works. So that is a linear activation function, basically no activation function, right? So just whatever is the output 120 here, pass it to the next layer. Just keep on doing that, right? Similarly, non-linear activation function, like you see G of Z here. So for example, sigmoid, that is 1 plus e to the power minus Z. That is a non-linear example of a non-linear activation function. So activation functions, to summarize it, it takes an input and it gives an output based on your requirement, right? So like I told you, right, based on your requirement, you have different types of activation functions. So I will explain you all of these activation. So let's say my use case is a binary classification example, right? So what focus on this part of the slide here, right? So if you see here, right? So my use case is to do a binary classification. I have three layers, one, layer two, right? And then layer three, right? Layer three comes here, right? So I have told my model that, my, let's not go into, CNN or DNN. Let's say or maybe, detecting spam or not. Let's say it is whether the email that I'm getting is a spam or a not, right? So I get inputs I process, and based on the sigmoid activation function, I will do a binary classification of 1 or 0, right? So the output layer, I tell my model that, do what? The first two layers, let it be ReLU. I'll explain you why ReLU, but this last layer, right? The last layer, as you all know, right? It decides the output of our model. So, put last layer as the sigmoid activation function. So now our model knows, okay, layer one is ReLU, layer two is layer, but layer three is sigmoid. So now our model now knows, okay, so the problem that you're giving is a binary classification problem. Let's say we are trying to predict something which goes into a positive scale and a negative scale, right? Maybe the temperature of your fridge, or maybe temperature of any place, temperature of New Delhi, or anything like that, any place that you want to predict. So that temperature, we usually, I mean, there are many activation functions. You'll see, linear, there are many different types of activation functions. But these are here just to explain you on the basic level. Don't get confused on them. They are very, very basic, and they'll help you to know what activation functions actually do, right? So I would say first, if you it is a natural human tendency to go and search, okay, what is a regression, what activation functions to use, if regression this value, what is ReLU, what is leaky ReLU, what is gradient descent. So the points told you in these slides are at the very base level. Once you have these strong, you can go ahead and tackle the higher problems, like what is a leaky ReLU activation function, or what is a softmax activation function, with more confidence, right? Because now we know what sigmoid activation function does. It is used when the use case is a binary classification problem. If you see here, it is based on the GZ value. It tells whether the value is less than 0, greater than 0, and it cuts it off there. Linear activation functions, like I told you, predicting, let's say, the temperature, it can go in negative and in positive scenario as well. It's what directly Wx plus B. G of Z is nothing, but it is, if you see here, right, Z is nothing, but directly that value itself. Now, there is one activation function, which is one of the most important, or like I would say widely used activation functions. This is ReLU activation functions. So ReLU activation function goes flat at one part. So if the value is less than 0, like if the value of Z, so Z is this W into X plus B. So Z is equal to this value, right? So Z is Wx plus B. So when we did this mathematical calculation, if Z became less than 0, it will give 0. If it is greater than 0, it will become that value itself. So if it is 100, it will give output as 100 itself. So that is how we define activation functions, right? So ReLU, sigmoid, let's say our use case is to predict the price or the temperature, right? So it will become linear activation function at the end. If we have to predict, do a regression value where the y is always greater than 0. For example, price of a house, price can never go in negative. Price of bitcoins, it can never go in negative, right? Yeah, so it is always greater than 0. So then we use a ReLU function. So this is how activation functions. So you must have seen what is this G of Z, we are putting it here, and then it is so confusing. Why is this function value being passed to a particular function? We did this all to understand why somebody uses sigmoid at the last layer, why somebody uses linear at the last layer, why somebody uses ReLU at the last layer, right? So now right, that your model is predicting the price of a house. So now that I have to use a ReLU function. Let's say you did the optimization in the previous slide. Your model still did not improve. So let's say you even increased or decreased your model still did not improve. Then you'll see, okay, maybe I saw there that ReLU is an activation function. Is there any other activation function? So now what ReLU does. You will try to appreciate, you'll be able to understand more about the other activation functions, for example, leaky ReLU or some other types of activation functions, right? So we use this to define our neural networks. Yes, so that is the end of our slide. To conclude, we learned about the basics of a neural network, how neural networks is took inspiration from neurons in a brain. What is the working of a neural network, right? We saw that how input is converted to an output, and we saw that each neuron, how does it passes the output of this neuron gets passed to the input of the next layer, and so on. So how this forward propagation or the backward propagation, how does that work? We got to know about that, right? Then we knew about the 3 general steps of training a model. We defined the structure of a model, we defined a loss function, and then we defined how to update these weights and biases. What is the optimization functions that we use? And then we learned about activation functions, right? So how do activation functions work, and what are the use cases of activation functions? Basically, we learned that every neuron gets an input and it gives an output. How does it give an output? It gives that output using activation functions. So, and we also know that different use cases have different activation functions. For example, we saw that different use cases like predicting the price of a house has a different activation function, and it has a different activation function when we compare it to a binary classification problem, right? So we learned about the basics of neural network, how to build that, how to debug it, how to optimize it. So now even if you see the code on, you'll be able, like I would suggest you all, go to Google, see the TensorFlow's code to how to build a very basic neural network. And you would now be able to, refer to this slide again, and you'll now be able to see that, okay, this is my neuron, this is activation. They have written sigmoid. Why have they written sigmoid here? So it will be very helpful to you in that scenario. And I think we are done here. So
Hello, sir. Sorry to interrupt. Can you please solve the doubts from question and session?
Yeah, for sure. Yeah. Okay. Let us.
Guys,
start.
before we proceed to answer your questions, I would like to request the attendees to please fill in the feedback poll so that it helps us to conduct more such sessions.
Okay, so let us start by answering an anonymous attendee's question. They are saying, what is the purpose of hidden layers, right? So like I told you, hidden layers are defined. It helps us to define our neural network, right? So hidden layer, we get an input. So at every layer, some processing is happening, some mathematical operation like we saw, right? W into X plus B is happening at that layer. So that means we are discovering more relations about that layer. So, for example, let's say we have a price of we have a house price prediction, right? So now we know that with the first layer passing, our model will discover more details about our data. With the second layer, our model will discover even more details, right? Once after doing this, once you go into CNN, you'll realize there are different layers. We do feature extraction. So layers, the purpose of hidden layers is to extract features and relations between the data and between the features, right? Yeah, how to know how many layers we need? It is usually, there are no set examples or no set values to it. It usually comes with as you learn, as you experience, right? You get to know that. So that's why I told you, go ahead, download a housing price prediction data set, right? And you can contact me on LinkedIn and I'll guide you through that. So, you'll know, right? Let's say you build with one layer, you'll see that, okay, my model is not working very good. Let's add 2 layers, let's add 3 layers. So next time, you go to a project or you are at a company, you know that, okay, I have to take these many layers, right? So it comes with experience, right? Somebody is asking, can you provide the roadmap to learn more about neural networks? Okay, this is a good question. So basically, first step would be, I would say, cover the basics. The basics need to be very, very strong. I have given so many interviews, and most of them, whenever I get rejected or whenever I was rejected in those interviews, I was mostly rejected because they told me that your basics are not clear, or you don't know what you have worked on. Like in the starting years, you have to, like, I always asked my interviewers that, what should I do next, right? They told me to make your basics very, very strong. Not only will they help you crack more jobs, they will also help you perform better in your current job, right? So first get the basics ready, then go towards, you did housing price prediction, right? You used a ReLU activation function. Now let's say you want to use a softmax activation function. Softmax activation function is again a question which somebody has asked. It is used in multi-class classification, right? So if I have to predict, let's say, values between 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, different classes, right? So then we use, you'll then go towards use this structure itself. You define the structure of a model, start changing the activation function, then start changing the epochs. So you'll know more about neural networks. Next question. Is there a way to know if the classification is binary classification or regression? Which algorithm function did you perform first in order to guide you? Okay. So basically, so classification is either binary or multi-classification, right? So binary means you have to classify whether this email is a spam or not, whether your credit card loan or your loan will get approved or not, right? Or whether this product will sell or not. So this is binary classification. So this is what, this is type binary class. What algorithm function did you perform first in order to guide you? I started with the very basic part. I started with, I started with, very, very basic linear regression. So that's how I knew that W, X plus B, where is it coming from? Then I moved towards logistic regression. Then I moved towards random forest. Then I came towards neural networks. And then I went towards recurrent neural networks, convolutional neural networks. So then I always believe secure your basics and then move towards the next step. Okay. Let's target new question. Somebody is saying, okay, this is a very good question. I'm a working professional and I have experience of 2 years. But nowadays we have pre-built architecture and frameworks for object detection, classifications, everything we do. Yeah, exactly. So like I told you, right, TensorFlow did your job so easily, right? You did not need to know what gradient descent rate. You just did you. Let's say I got my code from Kaggle or Google. I just copied it, I ran it, and my model ran. I'm happy. Okay, I'm a data scientist now. So, but now, this is a learning curve. This is a good point to start getting into the basics. Ask yourself questions, right? That, what is happening here? Why is it the activation function? Why only ReLU? Why not something else? Start asking yourself questions. Google is there. Type on Google and get your answers, right? And people are always there to help you out. Can you please explain the loss and cost function in intuitive way? Okay, so loss and cost function, I know the maths can be very tricky. Just see that our model will give an output and we have to compare it with the real value, right? My model told the house price of my house is 10 rupees. In reality, it was 100 rupees, right? So the loss will be, let's say, 90. So it is a very large loss, right? Or the cost is 90. That means the accuracy is just only 10%, right? So we have to improve it. So how will we improve it? We will use optimizations, right? I hope that answers your question. Are we getting any new questions? What is epochs? Okay, so epochs is like I told you, right? Gradient descent updates weights and biases. And how many times to run do that W is equal to W minus alpha. That is epoch. So epoch is 20 times, 100 times, 500 times. So update your parameters 20 times. So that is an epoch. And what is Keras in code? Is it a class or a function? Okay, I think I must have skipped that. Keras is basically again a sub-library of TensorFlow. It was an independent library in the starting. It is a sub-library now. So TensorFlow uses Keras. We do T and TensorFlow.keras to get all those, dense layer functions and sequential functions, model.fit. All those functions are part of Keras library. Can you give some examples how to fix the number of layers like I told? Computer vision problems, I would say first, if you have secured your neural networks, you know how they work. Building a CNN would not be a problem for you, right? So it would become very easy. But I would say again, if you know neural networks, how neural network works, go see what a CNN is, how convolution neural network works. And then you would start with a very basic, cat and dog picture recognition, and it will help you. Loss function and cost function. Loss is for a one record, like for my particular house, what is the loss? For all of us, what was the collective loss is the cost. Summed over all the losses together is known as cost. L1 plus L2 plus L3 till L, how many examples are there? That is the loss in a very simple and intuitive way. Are we getting any new example? Any new questions? I don't think so. Okay, what is gradient vanishing? What is descent vanishing? That is something very advanced for this class, but if you want to know, that is, we do a DJ by DW that we were doing. That is the gradient of your cost. And once your, the values, it becomes very, 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 very less, So the DJ by DW becomes very, very, very small. So, the updation becomes very slow. It is equivalent to no updation. Why do we need activation functions? Okay, we need activation functions. Basically, our neurons, each neuron gets an input. We get an output, right? So to get that particular output, which would suit our use case, let's say my use case is to predict the price of a house. So I would use a ReLU activation function. Your use case, let's say, is to predict the temperature in a particular city. So it can go to minus also. So you would use a linear activation function. right? Can I get a data scientist job as a fresher? Yes, you can. Obviously, we did get that. And try building your resume. Talk to more and more people on LinkedIn, and it will be helpful. Can we use some other algorithms other than ReLU and Sigmoid? Yes, we can. We can use some other activation function. That's what, like, right? You saw what Sigmoid and ReLU does. There are many different types of activation functions. There's a softmax activation functions. There's a ReLU activation function. There's a leaky ReLU activation functions. Now the activation functions are something which, like, there'll be so many activation functions, you'll get confused, right? So I would suggest first, have your basics very strong. What does Sigmoid do? What does ReLU do? What does softmax do? And what does linear do? I guarantee you 95% of your problems can be solved with these four activation functions. Some example to the computer vision. Okay, this question is being asked a lot. Can you give me some examples with use case of computer vision problems? Like, I'm not sure what this question actually means. If you want me to explain computer vision, I think we are out of time. But I would say, if you know neural networks, computer vision recognition usually works with something known as CNN, convolutional neural networks. Right? Go to Google and you'll know more about. It is a type of a neural network itself. That's why I told you neural networks are very important. CNN is again this type of neural network. This type of concept is again used, right? We get an image into RGB, and then we take that image. It gets passed through layers, different features, like let's say it's cat versus dogs. So let's say each layer knows, like let's say layer one knows that if the tail is very big, it's a dog, or maybe if it's very cute, it's a dog. So something like that. But yeah, so go more, know more about neural networks, and then start looking at more. You'll know more about them, about how CNN or image recognition works. Could you recommend a simple book on neural network? I would say do some good courses. Coursera is good. Deeplearning.ai is good. And yeah, Udacity is very good. Coursera, yeah. Those are the courses over there. They are very helpful. I did not refer any book. Do we have any more questions? I don't think so. So it was great talking to all of you. Thank you very much.
Yeah.